Okay, so let me go ahead and start recording. Today's lecture is going to be on trig substitutions, right where we left off yesterday. But as I was saying beforehand, let's go ahead and jump into one of these homework problems that is a little tricky. So this is homework 1, number 3B. So you want to do an integral of cosecant. And so the first tip is to use the tip on the homework. And then the other thing you're going to need is how to do the integral of cosecant. So you can check. The problem with cosecant is you might try a few things. Cosecant is 1 over sine. And we were looking at trig integrals yesterday. It's nice when we have sines and cosines, but again, we need like an odd power of one of those. And while we do technically have an odd power of sine, we don't have any cosines. So a u sub isn't going to work for this. You could try to do integration by parts, but the thing with integration by parts is that it is it's for multiplication, right? Integration by parts is the Leibniz rule. It's the multiplication derivative rule in reverse. And what do we have? We have a quotient, right? And so the quotient rule in reverse, we don't really have, there isn't an integral formula for or technique for. Usually you try to finagle it and use an integration by parts. But the only thing we could essentially do is set cosecant equal to our u, and then dv equal to x dx, or sorry, just dx. But then that would give us our v is x, and our du, what's du going to be? Negative cosecant cotangent.
It's negative, right? Yeah. Okay, cool.
Yeah.
I always mix it up if that's negative. But
Yeah.
That makes sense.
The cosecant and secant derivatives, it's easy to forget which one's negative. And so what's our problem? If we tried to plug this in our formula, well, we've got uv minus the integral of v du is now x times negative cosecant cotangent. So the integral we end up with after using integration by parts is more complicated than the one we started with. And so you can try it, and you could try to add some extra tricks and go from there, but you'll likely be spinning your wheels and you're going to run into a wall, and just it's going to get more complicated, more messy, and not going to work. So the only way to do this trick, or do this integral, is to know the trick, and we just multiply and divide I'm just going to call it a magic factor, which I'll write out here for you. So what we want to do is take cosecant of x. We're going to multiply and divide by cosecant of x plus cotangent of x. And now, what's this going to look like? We're going to have cosecant squared plus cosecant cotangent all over cosecant x plus cotangent of x. Now, why did that help us? Again, the integral looks a little more complicated, and usually if things start to look more complicated, it's not the direction we want to go. But in this case, it's magic. So I'll leave the rest for you to work out. all you got to do now is set u equal to that factor, or the denominator, cosecant x plus cotangent of x. And what happens when we compute the derivative, the differential? And then, oh, did we miss a minus sign somewhere? Derivative of cotangent is minus cosecant squared, yeah?
Yeah, it's negative.
Uh-oh. Hang on. Let's look this up. So the other thing to do is, when in doubt, look this guy up. Integral of cosecant. We were looking at this yesterday. I'm pretty sure it was a plus. Let me see if I got a minus sign wrong somewhere.
I think it should be like
I missed
negative
the minus on the
cosecant
first.
squared.
Yeah, that's what I did. So this is minus as well. Yep. And as someone mentioned in the chat, if it has co in front of it, the derivative will be negative. Good tip. So this one's negative. This one's negative as well. Negative cosecant squared dx. And now what's going to happen? This is the numerator up to a minus sign. And then this guy is our denominator. So that u sub will be a very nice u sub. And then when you integrate, you should get something like a natural log of u. So work the rest of that one out on your own. Again, there's nothing to memorize here. There's nothing to like actually teach with this integral. There's no real technique. It's just a trick. So I will try to fight for it to never be on a quiz or an exam. It's a nice homework thing to just work it out, right? It is nice to work out the integrals of all the trig functions, which we can do now. Do the integral of tangent. That's an easy u sub, cotangent. Of course, sine and cosine we know. And then even the arc functions, inverse trig functions. We did arctangent. I think arc sine is on one of the homework problems to do those integrals. You can do those with integration by parts now. But then the only ones that kind of remain are the secant and cosecant integrals. And unfortunately, the only way to do them is with a trick. So it's nice to work out at least once in this course, but they're not good things to have on quizzes or midterms. Okay, so let's try to finish up with some of these trig subs. And we only got a few minutes since the TA is going to come. We only got about 30 minutes. So I'll try to get through a few examples. And maybe some of these examples we won't actually finish. Some of them maybe we'll start the integral, and then I'll leave it for you guys to finish the rest of the integrals, plugging in the bounds and things like that. That stuff, you guys are all pretty solid if you're in this class at this point. So I'll leave those to your own work. Okay, so trig substitutions. Let's write down some useful things. The biggest thing we're looking at is our Pythagorean identities. So we've got sine squared plus cosine squared equals 1. And actually, more useful form, let's write it as 1 minus sine squared equals cosine squared. And of course, we can flip the sine and cosine in that case. The other one we have is 1 plus tangent squared is secant squared. And then using that same one, secant squared theta minus 1 is equal to tangent squared. So what's useful about these? Notice that it's a difference of squares. Then it goes to a single square. Here we have sum of squares. To just a single square term. So I was mentioning this yesterday. The key things about the Pythagorean identities and why they are useful is they can get rid of sums, especially if we're taking square roots and you see these sums underneath a square root. We can use these Pythagorean identities to essentially get rid of the sum and just turn whatever is underneath a square root into a single squared term. So likewise with this one, these two are going to be the most useful, difference of squares and a sum of squares. This one again is a difference of squares. The only difference between those two is that here our function appears first. Here we're subtracting off a function, constant minus a function squared. Here it's function squared minus a constant. So difference of terms to a single term. So let's take a look and do some examples. So we've got the integral of x cubed over square root of 16 minus x squared. And so the first thing, what you're going to want to look for is those exact notes. So the dead giveaway here is that we see the difference of squares under a square root. So we are going to use the difference of squares. And in particular, we've got constant minus a function. So we're going to use either a sine or cosine. I like to use sine just because derivative of sine is positive cosine. It's a little easier to keep track of the minus signs. So the problem is our constant isn't 1. Not a tricky thing to deal with, though, right? If I take this identity and multiply both sides by 16, we will have 16 minus 16 sine squared is 16 cosine squared. So with these, sometimes for me, I think when I first learned them, it's easier to almost work backwards. So I did this yesterday. What do we want? We want 16 minus 16 sine squared. But we have 16 minus x squared. So let's just make this our x squared. And so how do we figure out our substitution? You can start with we want x squared equal to 16 sine squared. Take a square root. That's our substitution there for x. And then now we can take a derivative to get the differential. So dx is 4 cosine theta. And so now our integral, we are going to have in the denominator, we'll have exactly what we wanted, 16 minus 16 sine squared theta. The numerator, we've got x cubed, so it'll be 48, 64. 4 times 16 sine cubed theta. And then our dx gives us another for cosine theta d theta. Okay, so finishing this guy off, shouldn't be too difficult. What's 4 times 64? That's what, 2 to the 6 times 2 squared, so 2 to the 8, so 256. 256, we've got sine cubed cosine theta in the numerator. The denominator now, we can factor out the 16. So square root of 16 is 4. And then we'll have 1 minus sine squared, which will give us cosine squared. Everyone follow me on that? So I'll do some of the algebra a little quickly. Just stop me if you're ever confused about a step or you don't see how I got something. So this one, just factoring out the 16 underneath the square root becomes 4. Gives us a 1 minus sine squared, making that substitution. And then, of course, the square root of cosine squared is cosine. So those two terms will cancel. And what are we left with? An integral of sine cubed. And so we saw how to do this one yesterday. Take out two factors of sine, make them cosine using a Pythagorean identity, make a u sub, and I'll leave that one for you guys to finish. Let's take a look at more of these, though. So some trickier things can come up with these trig integrals, and I just want to make sure we spend the time doing it. So I had quite a few examples to look at. Let me see. Let's do this one. Let's try to get 2 more in, at least set them up. Setting them up, recognizing what you're given in the integral.
A quick question.
Yeah.
So for the last problem, how do you substitute it back? Because we have to have it in terms of x, right?
Yes. We will talk about that. I wanted to do an example. Integral of sine cubed. This one had bounds. Let's do another example, and we'll see if we can get an easy integral. We'll do it. I'll try to do at least one to show you guys how to substitute back. We saw the example yesterday where if we have definite bounds, just like in u subs, you can change your bounds. So if you have definite bounds, change your bounds in terms of theta, I think is easy. But that is a good question. If we don't have definite bounds, we need to back substitute to make sure we get back in the x's. So let's see if we can do a complete one here. Again, some of these examples, since they require a lot of different techniques, sometimes they go quick, sometimes they can be lengthy. So we'll take a look at a new one. We've got x squared times the square root of 4x squared plus 9. So we look at the integral, and the first thing we see is the sum of squares. Also keep in mind, this usually doesn't come up, but constants, positive constants, are always squares, right? Even if it's 5, square root of 5 is square root of 5. And we can always do that. So usually we don't throw those kind of bad numbers at you and keep it naturally, integer squares. So we have sum of squares. We want to use our tangent substitution. And so what do we want? We've got 4x squared plus 9. If we want to use tangents, it would be easiest to have it as 9 tangent squared plus 9. So I guess we should maybe write it this way. What do we have? 4x squared plus 9. What do we want? We want 9 tangent squared plus 9, right? We want the constants to be the same. That way I can factor out this 9. Tangent squared plus 1. I can use trig identities to get rid of that sum. And so what's this tell us that our substitution needs to be? 4x squared needs to be 9 tangent squared. So here it looks like the constants may not be the prettiest, but this kind of illustrates the technique of how I like to set it up and how you can work with these constants. So that way you're not just guessing. Some people will just straight up say x equals something. And if you just start with what x needs to be, sometimes it's hard to keep clear. You know, it's easy to make a mistake with some of these constant manipulations. Setting it up like this, now I can just work out what the constants need to be. So x squared is 9 over 4 tangent squared. X is 3/2 tangent. So as long as your algebra skills are good, it's a much easier way to keep track of the constants and figure out what your substitution for x needs to be. And then, of course, we need the differential. Someone mentioned the trig identities. Yeah, so make sure you guys memorize those. This is pre-calc stuff. I can show them again. But the main ones we're going to work with are these two. So sum of squares, 1 plus tangent squared is secant squared. Difference of squares, either 1 minus sine squared gives us cosine squared, or 1 minus cosine squared is sine squared. Those are the biggest ones you'll use. This one will come up every once in a while. Okay, so we made our substitution, solved out all the algebra, computed our differential. Now we just plug it into the integral. So our dx is going to give us our 3/2 secant squared theta d theta. And then in our denominator, we've got x squared, so that'll give us a 9/4 tangent squared times the square root. And now nicely enough, right, we cooked this guy up, the substitution up, so that everything underneath the square root is this now, right? Our 4x squared is 9 tangent squared. And it looks like this integral may not be much easier. So maybe we'll have to do one. Okay, so let's keep track of the constants. We have 3/2 divided by 9/4 is times 4 over 9. Then we have this 9 here, which I can factor out under the square root. When we factor it out, it'll be 9 times tangent squared plus 1. Square root of that is 1/3, or a 3 in the denominator. And that's all our constants. So what are we left with? Numerator stays the same. Denominator, we have 1 factor of tangent squared. And then what do we get here? So we already factored out our 9. Tangent squared plus 1 is secant squared. Square root of that gives me 1 power of secant. Simplifying, looks like our constant is 2/9 times the integral of secant divided by tangent squared.
Wait, shouldn't the in the second row, shouldn't it be tan squared theta, secant squared theta?
Where at?
So scroll back down a little bit. not that one, the one right below it. Because you factored out the 9, shouldn't it be, because it's 1 plus tan 2 theta or tan squared theta, shouldn't the resulting factor be secant squared theta?
Yep. So secant squared, remember the square root there. Gives us just that
Okay.
one power.
Okay, got it. Thank you.
Yep. And you'll see a lot of these. Sometimes there's a square root, sometimes it's not. Always got to be careful with all this algebra. Okay, so how do we do this integral? This one looks like it's a little messy at the moment. Let's see if we can do this one and then back substitute to find our actual antiderivative. It might be a little messy though. So we have secants and tangents. Unfortunately, we don't have a secant squared. If it were a secant squared, it would have been nice because then I could make a u sub for tangent. Not going to work out quite that nicely. However, the tangents are in the denominator. So with something like this, what might be easiest, let's take a look and just convert everything to sines and cosines. So I'm going to write it as our secant is 1 over cosine. And then we have tangent squared, 1 divided by tangent squared. So that'll give us cosine over sine, or cotangent squared, right? D theta. And now we get 1 power of cosine to cancel out. And now this one looks like it'll be not too bad to do. So we saw these trig integrals yesterday with sines and cosines. We saw them in multiplicative form, but we can use some of the same tricks when we're dividing sines and cosines as well, as long as the differential is in the numerator. So this works out really well. We have sines in the denominator, and if I make u, a u sub for sine, derivative of sine is cosine, and that is nicely enough the only factor in the numerator. So with this guy, we're going to make u our sine, our du is cosine theta d theta. So that cosine theta d theta becomes our du, and we've got a u squared in the denominator there. All right, so we're still in there. Again, these problems, they can get rather lengthy. We are at an integral of 1 over u squared du, which we know is just going to be u to the minus 1 with a negative out front, and then plus our constant.
If you didn't put the constant in there, but you just sort of throw it in on the last line, do you reckon we'd get marked down in sort of tests and quizzes? Or do you think it's all right if we just sort of wait till the end to throw back in the C?
Oh, the plus c? Yeah, if you want to put it in at the very end for an indefinite integral, that's fine. The plus c isn't... I don't know how the TAs are going to grade, but I honestly don't care too much about the plus constants. It's not like a pivotal part of problem solving. Okay, so now we need to back substitute everything. So our u was sine theta. So that's our first one. So we're going to have negative 2/9. And this u inverse, always be careful with the notation. It is 1 over u. So this should be 1 over sine of theta. Just be careful with that. Don't write sine inverse. It's not arc sine. It's actually kind of bad. It's weird notation with that. So we've got 1 over sine, or we could write it as cosecant if we want. And now what do we need to do? We need to go back to our other substitutions. So let's write out our trig substitution just to organize our notes. So we had our x was 3/2 tangent theta. And so now our question is, how do we get back into our x's? Since it's an indefinite integral, we started with x. We want to end. Our solution should be in terms of x's. So what we want to do is take this and solve for theta. Or at least solve for the trig function involving theta. So we'll get 2x over 3, or 2/3 x, is tangent of theta. Once you isolate the trig function, the next step is to draw a triangle. So it doesn't matter what quadrant you draw the triangle, really. We're just going to have some angle in this triangle in standard position. And what do we know about this angle? We know that the tangent of this angle is 2x over 3. So tangent is opposite over adjacent. We need an angle whose ratio, tangent ratio, is 2x over 3. How do we find the other side, the hypotenuse? Yeah, let's call it h, actually. Pythagorean theorem. So that's our h. And funnily enough, what's that look like? That looks very similar, actually exactly similar to that same substitution we made. So this happens quite often. These quadratic expressions that we're substituting out are often one of the sides of these triangles that we end up with at the end. And so if we know our h, now we can compute cosecant of theta. So here's theta. Cosecant is 1 over sine, so hypotenuse over the opposite. So our hypotenuse, square root of 9 plus 4x squared, divided by our opposite side was 2x. Any questions on that? Someone mentioned in the comments they kind of missed on the last page. Is everyone good with this page? Or we can kind of go back over. So let's just kind of review this problem then and see all of our steps in case you missed any of it. So we're given our original integral. The thing we see a square root with a sum of squares underneath the square root. So 4x squared plus 9. So that's a dead giveaway that we want to use a tangent sub. We have a 4x squared plus 9. In order to use tangent squared theta plus 1, we need the constants to match up. So you always sort of match whatever this constant is with the 1, or multiply that 1 by that same constant, which means we also need to multiply the tangent by the same constant. We want 9 tangent squared theta plus 9. So if we compare these two, what's our substitution we need to make? 4x squared has to be 9 tangent squared. We go through the math to isolate our x. So that's our official substitution. And then that allows us to compute the differential as well. We go through, we make our substitutions, keep track of all the constants. I like to get all those out front first. Careful with the square roots. Those are easy to forget. Common mistakes are when you factor out this 9, forgetting to square root that 9. Remember, the 9 factor of 9 is under the square root, so it'll turn into a 1/3. And then we'll have tangent squared plus 1, gives us a secant squared. Again, it's under the square root, so that gives us a secant. Simplify things. Get it to a form where you can integrate or at least make a substitution. So we converted everything into sines and cosines. Since our secants and tangent substitutions in terms of trig integrals, that's not the best form. When secants and tangents are in a quotient, it's hard to see if there's a substitution that'll work straight from here. So sines and cosines worked better for us. We were able to make a u sub then, since we had 1 power of cosine. Easy u sub. Easy integral after that. And then back substituting everything. So the u's went to our trig, and then how we got our reverse substitution from our trig. Start with our x substitution, solve for theta or whatever trig function is acting on theta. So we just solve for tangent theta, and that tells us that we are looking for some angle whose tangent ratio is 2x over 3. Pythagorean theorem gives us the other side. And then now we can go back and see, well, if I have 1 over sine or cosecant of theta in my expression, I can then use our triangle, the defining triangle for theta, to figure out what now other trig functions are when they're evaluated on theta. So our cosecant of theta in this case was h over 2x, or square root of 9 plus 4x squared, all over 2x.
Would you not simplify that to maybe -1/9 and then just have it over x?
Oh, yeah, I didn't see that. Those will cancel, sure. 1/9 square root of 9 plus 4x squared, all over x. Good. Any other questions?
Yeah, I just had one quick question. Towards the top of that page. So you had u to the power of -1. Why is that not equal to an inverse function and rather just cosecant theta?
Right, it's this u to the -1 is 1 over u.
Got it. Okay. Thank you.
Yeah, so just be careful with that. The notation is similar. Any other questions?
If you wanted to avoid sort of confusion with things like that, could you not just go through and use sort of arc sines and arc cosines and things like that instead?
Right, I try to do that. I do that in the math department a lot with arc sine and arc cosine, and avoid the functional inverse notation because it can be confusing. Okay, so I think we need to get recitation started where you guys will get more practice with this. Unfortunately, I did want to do one more example. These can get even trickier with things like something like this. It's a little weird now that we're looking at it, right? We're usually looking for sum of squares or a difference of squares. Here, well, I've got one squared term. This could technically be a squared, but it's really our linear term, right? So what do we have to do in this situation? Everyone's favorite mathematical thing. We have to complete the square. So maybe we'll do this one tomorrow. We'll start with this one before jumping into partial fractions. I don't know how you guys feel about it, but I know that every time I've taught pre-calc, as soon as you get to completing the square, it's like everyone's brain just shuts off. Hopefully you guys won't be too bad on it. These examples, they don't come up too often, but maybe there might be one. So we'll start with something like that tomorrow and then do partial fractions after that.
A question on the last one. If
Yeah.
you were to use like inverse sign, like when you substituted it back in, would that kind of like destroy the bounds of the function kind of? 'Cause,
Yeah, I
like,
mean, it's the complete wrong function and the complete wrong integral.
okay, yeah, that makes sense.
I mean, it would just be like throwing natural log of x in instead. It's just
Yeah.
the wrong thing.
Yeah, it's just the wrong function. Unfortunately, I mean, there's a good reason why we use that kind of notation. It can be tricky though for young students when you first start to do it. Yeah, I guess another way to write it is, since u was sine of theta, we could write it as minus 2/9. It is sine of theta all to the -1. Not sine inverse, not arc sine of theta. It's actually kind of a problem, I think, right? Because there's a problem with this notation.
Oh yeah, I just meant like at the very end when we're trying to plug theta back in, and we decided to like solve it using the triangle and like comparing it. But if you were to solve it all the way for theta, and you like get an inverse tangent, and with a like a function of x within it, wouldn't, if you gave the equation in that form, wouldn't it kind of destroy the bounds because tangent of theta only goes from like negative 2 pi to 2 pi, or no, negative pi to pi, or
Yeah, I mean, that is one of the things that might go wrong. I mean, it is the entire wrong function, so you can't really draw triangles on it anyway. So like your arc sine theta wouldn't quite work the same way in terms of drawing a triangle, in terms of how it's defined. It would just, it wouldn't work. It's wrong. In any case, let's turn it over to Lewis. Lewis, you're here, right? I think I just made you host.
I'm here. Hello.
All right. So everyone, this is Lewis. He is our TA. He will be grading all your homeworks, grading all your quizzes, and administering the quiz. And I think that's it. You need anything else from me?
Nope.
Cool. So you are host. I'm going to leave, and hopefully, I don't think Zoom should crash, right? You should be able to just take over.
We'll all cross our fingers.
Yeah. So send me an email or something real quick if it crashes here. All right.
Okay.
I'll see you guys tomorrow.